The method of broadcasting for cycling competitions has traditionally been with a two-man crew or motorbike. Our project proposes a new solution. Motorbikes present a hazard to cyclists as they roll alongside and can collide, causing injury and damage. Drones, however, can remain attached to a motorbike, allowing the motorbike to maintain distance from the cyclists with the drone flying above and filming. Quadcopters, whilst available on the market, can create noise and distractions, which could be distraction to the cyclists during a race. Gliders are silent and can be tethered to a motorbike so that the power, signalling and broadcasting can run indefinitely. Our project aim is to develop a tethered glider drone to replace the motorbike camera for safer, high quality camera footage. Our project objectives consist of 4 key deliverables. The glider must be able to fly at constant velocity, change vertical flight path, fly at varying velocities within a designated flight path, and fly with a camera attached so that it may film cyclists during race events. The glider used in the project is the Crescendo Advanced Self-Propelled Glider with a propeller and attractor configuration. Early modifications include a tether attachment point for the tether to be attached to the glider, new autopilot electronics for stability in flight, and extended skid for camera clearance. The few structural changes include glue repairs made to repair foam, an added GPS, circuitry and antenna on the exterior, reinforcing between the nose and fuselage using a carbon fibre tube and steel wire, and a landing solution consisting of skids and wheels across the duration of the project. Most modifications are formed from 3D prints, including the skids, covers, nose tip and tether lid. Some, however, were not strong enough and are replaced with metal or composites, including the landing gear from steel, reinforcement and tether attachment, which was made of a steel ring. The latest glider configuration is stronger but heavier than the original, requiring greater speed for takeoff.
The project management timeline is reviewed from the Capstone Project A and amended based on the constraints identified and serves as our timeline for Capstone Project B. The electronic system of the glider comprises of these components: servo, ESC or electronic speed control, battery, autopilot, GPS or global positioning system, transmitter and receiver, binder transmitter, and MPU or modular power unit. A conventional RC battery is used. The use of ESC or electronic speed control and MPU or modular power unit is important to power the servos and the autopilot. The components are assembled and tested based on the electronic circuit diagram. Mission Planner is the software used to calibrate the autopilot, which laterally and vertically stabilizes the control surfaces to achieve steady-state flight. A bicycle is used instead of a motorbike for testing purposes. The bicycle is a fixed gear type with a gear ratio of 51:23 that will achieve the average speeds of 26 km/h easily. It is fitted with a rear rack to accommodate the mounting arm that will attach the tether to the bike. The flight test was conducted 4 times over the course in the Capstone Project B. The first 2 flight tests were conducted on an artificial grass surface with the objective of achieving takeoff for flight. The third test was conducted on a concrete surface with the objective of achieving steady-state flight after takeoff was accomplished in the first 2 flight tests.
Based on observations from the initial flight tests, a few modifications were made to improve the glider's performance. Number 1, we replaced the rigid stiff tether, which we originally were testing with a bungee cord featuring hooks at both ends for easy attachment. 2, we used a metal ring for the tether connection point. Thirdly, a carbon fibre rod was used to support the frame and minimize damage. And lastly, we added fixed flaps to lower the speed and increase the lift. This all led us up to the final flight test. Wait, it's actually going. Look, wait. Wait. Yeah, keep this way, keep going.
As can be seen, the glider achieved steady-state flight for a sustained period of time. It was done at the velodrome, which contained banking angles to achieve average speeds quicker.
From the testing, it was found that the glider can fly in a straight, level flight path whilst connected to the tether, and that the camera can be mounted successfully. Thus, we can conclude that the concept is feasible, however some safety issues are of concern. The tether tangling, the mounting arm and glider swinging around bends, and the glider crashing, leaving debris on the track. Our early concept covers two of our objectives: steady flight and camera implementation, with others yet to be explored. Ultimately, it was able to fly, but it needs development. We envision a developed concept having attachment to a motorbike for higher speeds, purpose-built, stronger design with a landing gear, some form of auto tether release, camera upgrades with wireless features, and a gimbal for stability. Main power to be provided through the tether with a small internal battery on board for redundancy. Programmable flight envelopes for specific courses and obstacle avoidance. And lastly, a ground sensor to avoid collisions when flying at low heights. In addition, the tether mounting arm can be automated so it rotates about 2 axes to provide better tether control and therefore glider control.
In conclusion, 2 out of 4 key deliverables were accomplished, which are able to achieve steady-state flight and able to change the height of the flight. The other 2 were not achieved due to time constraints. However, the results demonstrated as a concept, a towed glider was feasible with time and effort.